Hi, everybody. So I'm thinking today I'll be the only one talking about simulations. First of all, thank you to all these people who, over the last 3 years, have evolved this from a 1D weekly line to a full 3D model for Reiner Gamma. Also, thank you to make me work on my national holiday. So, as we all know, for the last 40, 50 years, the moon does not have an intrinsic magnetic field. It does have regions of local magnetization, which we call lunar magnetic anomalies. They are very non-dipolar, and non-dipolar is probably kind of giving it too much credit. It's kind of a big mess. For example, this is the Gerasimovich anomaly generated by the observed magnetic field model, which we'll also use later on. A very small scale, like 400 kilometers across for a big region. Typically, they have a few hundreds nanotesla in strength. We don't really know where they're coming from yet. But maybe more important for today is there has been a correlation suggested with lunar swirls. So as we all know, lunar swirls, there are these high albedo markings on the moon, and all of them, as far as I know, have been associated with LMAs. However, the opposite does not hold. And this actually, at least in my view, it makes things a little bit more unpleasant than they should be to find the one, because if for every swirl we would have an anomaly, an opposite, problem solved, right? Unfortunately, this is not the case, so we need a kind of a model which works for all. So the three competing mechanisms at the moment is solar wind standoff, basically saying that these little magnetic fields, they're capable of locally shielding the solar wind, and the shielding pattern then, surprisingly, is the lunar swirls. Quite similar, there might be comets and micrometeorites impacting the moon. They pop out ejecta, they fall back down following the field lines, and you get the swirls. Similar thing is you can have dust popping up, and that this is actually possible has been proven very recently by Xu Wang and his lab in Boulder. There's these very nice movies. I think you saw one this morning where we can manage to pop up dust and let it land. But what I find so far in the simulations is probably a little bit of everything. So at first thought, you think, oh, well, maybe it's not so bad, this solar wind standoff mechanism. And for example, this is a very, very early simulation where I just took the head of Reiner Gamma and put a simple dipole, and you kind of more or less see that it could work, right? Also for me, is there a relation between ion reflection and surface shielding, formation of mini magnetospheres? Who knows? Because if there is a nice correlation, you can just like happily fly over, observe reflected ions, and then know what's going on the surface. So the thing I want to look at today is Reiner Gamma. I'm sure you've seen this one before. It's been discovered quite a few centuries ago, and it's one of the strongest LMAs on the lunar surface. Previous work has done this, or has approximated this thing by two dipoles, one sitting over this bit, and another one sitting more there. And I will show you later that this is not such a bad comparison. So how does Reiner Gamma look? Just visually, and this is a picture I stole from Andrew's paper. I think it's quite popular today. I think I've seen it before. So you have literally these two dark lanes there, which are these ones, and surrounded by bright lobes, like the brightest one's on the outside, and then a brighter one also on the inner side. The tool I'm using is iPic 3D. Has nothing to do with Stefano Marchida's affection for Apple products, but just simply stands for implicit particle and cell. Added to that are open boundaries, allowing for a flowing plasma, and the observed magnetic field model developed by Tsunakawa et al. So what is this thing? This model, it's basically, these guys took the 5 million observations from Kaguya and Lunar Prospector and did some horrible algebra on it, which they with a very nice word called surface vector mapping. They corrected this observed field for the solar wind pressure and the interplanetary magnetic field. And they say in their paper it's kind of okay to use it up to 6 kilometers above the surface. Today, however, I will use it all the way until the surface for the lack of anything better. So one thing that kind of is also unpleasant about this is, as you see, or as you might know from previous work, is that the solar wind interacting with these little tiny magnetic fields induces its own fields. For example, wrong button. For example, this one here, you get an induced electric field, which then also distorts your magnetic field. And this is something which is not incorporated in this model, of course. So this is how this model looks for Reiner Gamma. We have basically here the two strongest regions, which hopefully then correspond to these bits. I did not put in the IMF field just because it will complicate things a bit more. For those interested, these are the simulation parameters. So, and this is what comes out. So if I use this field, I have a solar wind coming straight from the top down. I find indeed sort of more or less something which you might say, oh, this looks like Reiner Gamma. You find indeed here sort of a shielding region, another shielding region. And actually, there is a little bit of a third shielding region here. And on top of that, if you look at the field, the compressed field after the solar wind is switched on, you see, well, this kind of looks like a dipole, also a dipole here, so it doesn't, maybe it's not so bad. Another thing you see is that although Reiner Gamma is quite stretched out, you don't really see much happening except for here in this central region. Okay. Good. So if you compare a bit more what's happening, we seem to reproduce kind of the large scale features, at least of this part of Reiner Gamma. Everything else here, although there is a little bit of patches of magnetic field there, we don't really see anything happening in our simulation. Zooming in a little bit more, you might even say that, hey, we see this little bit there, which might be like this. We see these two little bits there. Maybe it's this bit, but we don't really know. So I think there are two possible reasons for it. Either it's just this model is not accurate enough, which might probably well be. But secondly, I also think it'll be very, very hard just by pure having the solar wind standoff reproduce all these little tiny features, because you need quite a big magnetic field strength for that. So if you really want to have this kind of very narrow lines, you should have at least 400 or 500 nanoteslas. But if that were the case, we would see it higher up as well. So maybe there's something else responsible for that. Just out of curiosity, because of course here you see this bright lobe here, there's very bright lobes outside, and the dark lanes there. You don't really see them here, because this is just ion density. So you see shielding here and then more ions hitting the surface further out. Just out of curiosity, this is the total charge density, meaning that 0 means that you have the same amount of ions and electrons hitting the surface. Negative means you have more electrons hitting the surface, positive, or red means you have more ions hitting the surface. And then curiously enough, you have here these two blue stripes, which might actually correspond to these dark lanes with a little bit of fantasy. And what these two blue lines actually are is our regions of vertical magnetic fields, which not only have ions hitting to the surface, but actively also swirl down electrons. Good. So, but I think we just need more data to figure this all out. I can sort of hand waving say, hey, look, it looks a bit like Reiner Gamma, maybe not. But so far, with our data available, we can't really say much more than that. One extra thing I would like to show you is what happens if you look at the reflected ions, because hopefully this is something we can observe, right? You find quite a complicated structure, but if you add it all up, you see that at some spots more than 50% or even almost 100% of the ions are unable to reach the surface, which is in excellent agreement with also what Kaguya and Artemis observed. But more importantly, there seems to be kind of a correlation between where this reflected flux is going versus the magnetic field structure underneath. Let me maybe first show the next plot. So if you have more vertical fields, this is just a simple vertical dipole, you see they have more electrons just go almost straight up. And in this particular one, it was like 25% go straight up. Whereas where you have horizontal fields, which are actually the fields which shield the surface better, there is almost nothing, like a few percent, which goes straight up, but most of it goes to the sides. Wrong direction. So going back to this one, you can also see just by looking at the reflected population from the top, you see that here over this large dipole region, you see that there are these two big wings. They're not so clear on this plot, but it's basically that one, which go all the way sideways. Similar for the smaller one. Whereas here there is line which a little bit of more verticalized and they go more straight up. So maybe you can find some kind of a correlation between what we observe from the reflected population and how the field actually looks underneath. So modeling is very important here. To conclude, I think, unless I'm wrong, this is the first full kinetic simulation of the solar wind with an observed crustal field. We kind of reproduced the Reiner Gamma swirl, at least the large-scale features. I think that just looking at reflected ions, you might find there a tracer for the underlying magnetic structure. But all in all, I think we just need more data to be able to constrain. If you want to know what's going on with these swirls, just go there, put on your hiking shoes, walk around with a magnetometer, and then you will find it. And I'll be happy to do that, by the way, if you need a volunteer. Thank you. That was my goal.
Okay, that was a fun discussion. Let me add another thing to the pot. Coming back to the M-cube data, and in particular with the conversation we just had in the previous speaker, you probably know that initial analyses suggested that the swirls were sufficiently protected from the hydrogen in the solar wind so that the OH was lower.
Uh-huh.
The difficulty, especially at Reiner Gamma, is that it's right in the equatorial area, it gets hot, so for all the reasons that we discussed in the previous speaker, the OH and the surface, it's hard to study. However, that's just because of at Reiner Gamma it's difficult. There are at least one area on the moon where we had our high-resolution M-cube data, and the geometry was such that it was not as harsh. This is in the Marginis swirl area. And with those data, there's no question that the bright areas have a lower abundance of OH than the darker areas. So this really, somehow it feeds into whatever your modeling is, that we know there is some protection of hydrogen for the bright areas. And I don't know how that can feed into your models, but it would really be nice to see.
Well, I guess it's simply just changing the location of where my simulation happens. And actually, you're talking about Mare Marginis, right? I actually have that one in the pipeline. So hopefully in a few weeks, I might actually show you these results.
It's complicated because it's in a highland area.
Uh-huh.
And so you have a different composition of the surface to start with. It's more feldspathic, so it's
I don't care about that. So.
But from the mechanics of it, it really, the feldspathic versus basaltic may have a important OH relation. Cool.
Great.
So I didn't understand whether you had averaged all the solar wind incidence angles or you were only using one.
So far, this one is just one. The reason why I haven't shown you the integrated ones yet is because Pleiades, the cluster I'm running on, does not like imaginary directories, I noticed. So I hope to have them ready by today, but I have to rerun them because something went wrong.
I think previous work has shown that you can get very different patterns.
Absolutely, yes. I think I showed you this plot last year, indeed, yeah. Go for it. I made my talk short so that people could ask questions.
Are you from Norway?
I am from Belgium.
Happy Prince Haakon's Day.
Thank you.
All right, let's thank our speakers.